Cornell University Unmanned Air Systems is an interdisciplinary student project team that designs, manufactures, programs, and flies a custom-built unmanned aerial system. More than that, CUAir is a family. We learn, laugh, and grow alongside one another as students, engineers, and individuals. Since 2022, it has been a dream of CUAir to successfully design and implement a vertical takeoff and landing, or VTOL, system, which we named Artemis. Since Artemis's first design iteration, conceived during the COVID-19 pandemic, our team has worked through a variety of hardships and setbacks to improve the system's capabilities. As a result, this year we are more proud than ever to introduce Artemis V2, CUAir's 2023 aircraft. Developed by over 50 undergraduate students from a variety of disciplines, the aircraft is composed of a custom fully composite airframe and includes 4 vertical propellers for VTOL functionality, a custom 2-axis camera gimbal, and a parachute drop system for payload delivery. CUAir is confident in Artemis's ability to efficiently and accurately achieve all SUAS competition objectives. CUAir's 2023 flight line. Jack Williamson, Safety Pilot, Imaging Systems Lead, Class of 2024. Aidan Zamorsky, GCS Operator, Full Team Lead, Class of 2023. Owen Sorber, Imaging Ground Server Operator and ODLC Coordinator, Full Team Lead, Class of 2023. Polina Ermoshkina, Team Captain and Mechanical Supervisor, Full Team Lead, Class of 2024. Ibiyemi Abiodun, Imaging Plane System Operator, Imaging Systems Member, Class of 2023. Sean Yu, Airdrop Coordinator, Structures and Payloads Member, Class of 2023. Ashley Zhang, Electrical and Antenna Tracker Supervisor, Electrical Lead, Class of 2024. Eric Kim, Autonomous Vision Supervisor, Intelligent Systems Member, Class of 2024. Time to fly with CUAir. Acceptance criteria and design overview. The mission demonstration simulates a search, delivery, and rescue operation. Within the mission requirements, CUAir has established acceptance criteria for what the team deems a successful mission, and has determined system-level requirements for achieving these criteria. For the timeline task, the team has set a mission flight time goal of 25 minutes to allow for 10 minutes in vertical hover mode and 15 minutes of horizontal flight, thus requiring a cruise speed of at least 18 meters per second. We also require that no timeouts are taken. We plan to use one other operator in addition to the safety pilot and GCS operator to earn as many points for the operator's category as feasible. To achieve SUA's flight requirements, our system must also be capable of fully autonomous flight and turn with a bank angle of at least 50 degrees. Successful airdrop will entail full points on both of our 2 payloads. To do so, we aim to classify targets manually with 100% accuracy, and for our autonomous vision system, to identify at least 75% of targets and images as regions of interest, and correctly classify at least 80% of these targets. The hardware, electrical, and software systems of Artemis have been designed with these acceptance criteria in mind. 4 vertical propellers allow for VTOL, while a pusher propeller enables the transition to horizontal flight, and wheeled landing gear supports both vertical and horizontal landing. A custom 2-axis gimbal minimizes vibrations and allows for precise camera orientation. Payloads are delivered through bay doors in the fuselage. The electronics bay, or E-bay, holds batteries, custom PCBs, and the Pixhawk Cube flight controller. The Pixhawk controls the plane's flight and the airdrop system. A Raspberry Pi Model 4B interfaces with the Pixhawk and controls the camera and gimbal system. When images are captured, they are automatically geotagged and saved to the Imaging Ground Server, where an operator can manually identify objects or confirm classifications made by the Autonomous Vision System, AVS, then send the results to the autopilot system for airdrop. The AVS uses heuristics and machine learning algorithms to first detect regions of interest containing targets, then classify target shape, alpha, and color. To accomplish autonomous flight and waypoint objectives, we've created a custom version of the ArduPilot flight controller firmware. A custom web browser-based ground station built on top of the open-source Mav Proxy ground station allows the operator to monitor mission progress and set mission waypoints. Aircraft. At 2.22 meters in length and with a 3.67 meter wingspan, Artemis is CUAir's largest and most complex airframe to date. The system's 5 propellers are powered by 6 6S 8000 mAh LiPo batteries. The airframe is manufactured completely of composite layups consisting of a layered construction of carbon fiber face sheets and aramid honeycomb core to optimize its strength-to-weight ratio. In addition, the inverted U-tail design raises control surfaces out of the turbulence caused by the pusher propeller. To improve aerodynamics, the fuselage was created with a surface loft over a series of airfoils of increasing size from the wing root to its apex, making the fuselage a lifting body. Original designs utilized skis for landing, but the team decided on wheeled landing gear as an extra safety precaution to allow for horizontal landings in the event that vertical propeller control is lost. The team also changed airframe designs to allow for continuous spars through both wings, which support the wing load we required. In addition, the control surface materials were switched from balsa wood to 3D prints and carbon fiber to decrease weight and make the parts more manufacturable. Safety was also a major argument for developing a VTOL plane. As demonstrated during a test flight in late March, vertical propellers allow the plane to safely descend if horizontal motor issues occur. Such contingencies were an important consideration when designing Artemis. To verify Artemis's ability to meet all flight performance requirements, a variety of tests were conducted on both the ground and in flight. Materials testing for properties like tensile strength were used to determine the best 3D printing filaments and carbon fiber fabric to use for various parts of the plane. A custom rig to test wing loading was also employed during developmental testing. Test flights were conducted to verify turn radius, flight time, angle of climb and descent, and runway space, and found that Artemis meets all requirements. A total of 32 flights were made, for a total of 1 hour, 59 minutes of flight time. Autopilot. The Artemis system uses the Pixhawk Cube flight controller, with a full sensor suite including compasses, GPSs, gyroscopes, and accelerometers for autonomous navigation. The team uses the open-source firmware ArduPilot for its robust developer support and for the inclusion of many essential flight features, such as waypoint navigation, VTOL flight modes, and robust failsafes. The Cube runs modified ArduPilot 4.3 firmware, with additional features including support for our custom-made PCBs, and a custom payload drop algorithm enabling pinpoint airdrop accuracy. CUAir developed a proprietary ground control system, or GCS, to enable convenient and simultaneous control of aircraft vitals, flight mission progress, and waypoint navigation. Centralizing live flight statistics and waypoint information in one interface is critical to our team's efficiency and success in the mission demonstration. The GCS allows the operator to manually input waypoints during setup time, as well as during any point in the mission. The GCS operator also maintains the ability to terminate flight in accordance with SUAS safety requirements. Path planning algorithms were developed to autonomously create waypoints over the airdrop boundary as information is received on target geolocation. Artemis's autopilot system was rigorously tested over 32 flights, with a total of 1 hour 59 minutes of flight time, with 1 hour 22 minutes in vertical and 37 minutes of horizontal flight time. Of these flights, 8 were autonomous, with an average of 2 minutes spent in manual mode per flight. Waypoint navigation was also tested during these flights, with 80 waypoints hit out of a total of 87, and an average waypoint miss error of 17 feet. Imaging and ODLC. CUAir's imaging system controls Artemis's camera and gimbal, tracks the plane's location, and relays image data to the ground server. At the center of the imaging system is a Sony R10C camera, which has a 20 megapixel resolution and a focal length of 16 to 50 millimeters for zoom. Furthermore, a custom-built gimbal keeps the R10C facing perpendicularly to the ground to maintain uniform image perspective. A gimbal board communicates plane orientation data to the gimbal to ensure the desired angle. To calculate the location of a ground target, Artemis uses current flight location and orientation information from the Pixhawk, as well as the target's position within the image. Because this operation requires images and location data to be captured at the exact same time, Artemis uses a custom fabricated current sensing board to measure power draw from the R10C, logging the exact timestamp that a shutter click causes a spike in current. Once the ground server receives images, the Manual Vision System, or MVS, allows an operator to manually identify objects and assign each sighting to the corresponding water bottle payload. Any repeat sightings in multiple images are merged into one target. Once an object is tagged on the UI, the MVS sends the correctly identified targets to the Autopilot GCS for utilization in the airdrop task. The tagging procedure can be time-consuming, so CUAir has designed an Autonomous Vision System, or AVS, to detect and classify objects autonomously. The AVS receives images from the imaging ground server and starts by detecting ROIs using the MASK RCNN algorithm. Once an ROI is identified, UNet segmentation generates a shape segmentation. Further algorithms use these contours to classify the target's shape, alphanumeric symbol, and colors. If the resulting classifications have high confidence levels, the ROIs and their classifications are then sent to the MVS to provide tagging assistance to the operator. Our imaging and ODLC systems underwent significant developmental testing on both Artemis and testing platforms. Developmental testing was conducted on 60 target sightings using our DJI Matrice test platform over several flights. The average geolocation error was 11 feet, with a standard deviation of 3 feet, and 90% of targets geolocated within 15 feet. When tested on Artemis with gimbal and current sensing board capabilities on 44 target sightings, our performance improved to an average geolocation error of 7 feet, with a standard deviation of 3 feet, and 100% of targets geolocated within 15 feet. Communications. Artemis's communication system allows operators to send instructions, receive data, and control the plane system. The GCS passes MAVLink messages with the plane over a 900 MHz frequency for telemetry data and commands. A separate router and 5.8 GHz Wi-Fi network is used to send images from the plane to the imaging ground server and the AVS. The router connects to the GCS as well as the nanostation, a transceiver mounted on the antenna tracker that communicates with the rocket AC on the plane, so that all computers are connected over Wi-Fi. Tests were conducted on the communication system to test Wi-Fi range and throughput capacity. On average, the nanostation and rocket were able to communicate with each other in Artemis flights with a throughput capacity of about 100 megabits per second. The Wi-Fi system was stress tested at up to 1 kilometer, and sufficient throughput capacity was observed. On board Artemis, approximately 97% of images sent to the ground were received, with a median send time of 300 milliseconds, indicating low packet loss. Airdrop. Artemis's modular airdrop system carries 2 payloads, each housed in a 3D printed chamber and secured with easy-to-remove Velcro straps. Bay doors on the underside of the fuselage are opened and closed with a servo, and a pin mechanism controls payload release. During airdrop, the autopilot software commands a custom airdrop circuit board to open the bay doors and release the appropriate pins. To control the descent, each bottle chamber has an electronically controlled parachute release mechanism to guarantee consistent delay for parachute deployment. Optimal drop time is calculated by autopilot using aircraft speed, and wind direction. Several alternatives were considered when designing the airdrop system. One suggestion included a winch mechanism to lower payloads to their target while hovering overhead. However, this will require more vertical flight time and increase aircraft weight. A drogue chute specifically folded to delay opening was also considered, but this was proven to be inconsistent during testing. In addition, although the fuselage has the capacity to hold up to 4 payloads, the team ultimately decided to only attempt 2 drops to reduce overall weight and mission time. The team tested the airdrop system on smaller RC planes to fine-tune drop mechanisms and develop a model for calculating optimal drop time. A GPS mounted inside a bottle was used to test drop accuracy and provide more data with which to create the model. The team dropped 21 payloads, and the system released the payload 84% of the time. In tests on Artemis, the payload landed a mean distance of 9 feet from the target location, with a standard deviation of 3 feet, and 90th percentile distance of 16 feet. 83% of drops were considered successful by mission requirements. All payloads remained intact upon landing and were easily retrievable. Obstacle avoidance. The team decided to implement a button on the autopilot GCS that allows the GCS operator to command the aircraft to autonomously avoid any upcoming obstacles. The stream of an FPV camera on board Artemis would display the perspective of the plane on the GCS. In the event of an upcoming potential collision with another aircraft, the operator will be alerted and will command an update of the waypoint path to perform evasive maneuvers. Pressing the avoid button will autonomously divert the aircraft to a new path to avoid a collision. The team initially considered devising an autonomous obstacle avoidance system based on utilizing radar detection of other aircraft, but decided this would be very complex to implement and opted for our current system instead. Artemis's waypoint-based obstacle avoidance system has been tested with a total of 10 avoidances in 10 different simulations, successfully achieving an average course redirection of 10 meters in 5.5 seconds. Given our measured waypoint accuracy, we are confident in Artemis's ability to avoid all other systems at competition. Mission testing. The team proceeded to employ full mission tests to assess the performance of the integrated Artemis system at achieving each of the mission objectives. CUAir conducted 1 full mission test and estimated scores using the rubric provided in the SUAS rules. For the timeline portion, the team scored an average of 26%, taking on average 15 minutes to set up and 22 minutes of flight time. The team expects a similar time at competition. CUAir transposed multiple loops of last year's competition waypoints over our local airfield to simulate the waypoint requirements of the mission. Waypoint navigation and autonomous flight were achieved reliably, as they were in developmental testing. Since mock payloads were used in developmental tests, there were few aerodynamic changes to the integrated system, and thus, no corrective action was required to improve performance. The team expects similar performance at competition. Manual ODLC with autonomous aid was performed in all full mission tests with full success, with only 1 operator needed. Air delivery was tested with an average score of 40%. The team expects similar performance at competition. The full mission test score was 58%. CUAir has demonstrated that it can operate safely and professionally during the mission, and hopes to achieve full marks for operational excellence. CUAir expects to score approximately 58% of total mission points at competition. We'd now like to show you Artemis in action. Please direct your attention to our proof of flight. Manual takeoff. (1,000 feet from the safety pilot). Manual landing. Autonomous flight, 200 feet from the safety pilot. Transition to manual mode. Manual landing. Manual takeoff. Autonomous flight with all flight performance requirements. Manual landing. Artemis is the culmination of 2 years of engineering, trial and error, and resilience from the CUAir family, working together to realize a shared vision. Our commitment to excellence underlies the constant redevelopment and extensive testing that our system has undergone. As a result, we have high confidence that Artemis is capable of all mission requirements and will perform at competition as well as it has in testing. Thank you for flying with CUAir.